our test was based on 4 questions from the textbook, which is this one. The 4 questions are: what dryness? Questions are as follows from chapter 14. I'll read you the first one. A reaction A plus B goes to C obeys the following rate law. Rate is equal to K times A concentration squared times B concentration. Question A, if A is doubled, how will the rate change? Will the rate constant change? Explain. Part B, what are the reaction orders for A and B? What is the overall reaction order? And part C, what are the units of the rate constant? So we're starting with this reaction. Rate is equal to K times the concentration of A times the concentration of B squared. That looks like a Z. So I asked you for an explanation using words. So I wrote the following. If the A concentration is doubled, the rate will quadruple. I'm going to use red to show which parts I was looking for in the answer. The rate constant stays the same because it's the rate constant. What will cause a change in the rate constant? What do you need to do to cause the rate constant to change? What condition must you change to affect the rate constant? Heat, right? Raise the temperature, it raises the rate constant. Roughly 3.7 times faster per every 10 degree Celsius change in temperature, according to the Arrhenius equation. I'm going to say the rate constant stays the same unless there is a temperature change. So the rates change is caused by changing concentrations of A and B. And we write square brackets around things because it signifies what? What does that square bracket mean? Concentration of. Okay, so when you put that square bracket, it means concentration of. So concentration of A, concentration of B. Part B of the question asks, what are the reaction orders for A and B? Well, because they gave you the rate law, all you have to do is look at it. For A, it's to the power of 1. So with respect to A, the order of the reaction is 1. With respect to B, the order is 2. The total order is the sum of all those powers. So the overall order of the reaction is 1 plus 2, which is 3. So first order with respect to B concentration. Second order with respect to A concentrations. Third order.
Sir?
Yes.
You wrote it wrong.
Which one?
It's R equals to K A squared and B. So.
A squared.
Yeah.
Right. Thank you. And third over overall.
Okay, so I was looking for those three statements made. So when I marked it, I attributed 3 marks to the first thing, to the first statement about if A is doubled, the rate will quadruple. The rate stays constant. I was looking for some reference to that. And finally, only temperature change will affect K. So this part was at 3.
Hi, Mr. Bossy.
Hi.
Hi, sorry to interrupt. Could I see Chelsea, Fouquet, and Francesca very quickly united?
Okay.
Thanks so much.
You're welcome. I was looking for 3 statements like this as well. So that would have been 3 as well. So overall, okay, the last part we haven't done yet. That's the one that involved the most math. Let's get a better red marker though. That's a good one. For part C, you're asked to find the units of the rate constant. So, yeah. We start off with the reaction R. The rate of the reaction is equal to the rate constant K times the concentration of A squared times the concentration of B. We're going to solve for K. So we're going to transpose these 2 things and put them under there, and we'll get this. Then we're just going to put in what the units are for each one of these things. Rate is usually described in molarities per second, and concentrations are usually in molarity. So this one's going to be molarity squared because the whole thing is squared, not just the number, but also the units. And this is in molarity. So if we rewrite this fraction, this is a fraction over a fraction, so I'm going to write it as multiplication. This turns into molarity per second times 1 over molarity cubed, because molarity squared times molarity to the power of 1 is molarity cubed. So the molarity is partially canceled. And what you get finally is molarity to the -2 is seconds to the -1 is your final answer. But I'll show you how I attributed the marking. Now, if you went to the back of the book, you would have gotten the answer. The correct answer at the back of the book would have gotten you 4 marks. So I was looking for this initially. Oh, of course, I looked for the best one.
Mr. Bossy?
Yes?
Can you send out Mark Augustine, please?
Okay. For each one of these, I was looking for the proper transposition of variables to solve for K, the proper units substituted in, then the arithmetic that leads to the final answer. The final answer has 4 things in it, so I gave 4 marks for that. The total value of that question was 16 marks. So if you wrote just the last part, which you could have gotten by looking at the appendix at the back of the book, you got 4 marks. So total question value is out of 22. Question number 2 is from 28 in the book, and it says the reaction 2ClO2 aqueous plus 2-hydroxide aqueous gives you ClO3, chlorate. So chlorine dioxide plus 2-hydroxide gives you chlorate anions plus chlorate anions plus water. This reaction was studied with the following results, and it gives you 3 experiments where they vary the concentrations of chlorine dioxide and hydroxide. Notice it's chlorine dioxide and not chlorite. If it was chlorite, it would have a -1 charge, but it's ClO2 with no charge, so that's chlorine dioxide. Again, I was looking for a word explanation. I didn't want the novel, but just simple words explaining what was going on. So, in experiment 1 and 2, the OH minus concentration is constant. So it has no effect on the rate. Therefore, no effect on rate. The key to solving all these scientific problems is to break them up into small enough pieces. You can't have a sort of global, well, maybe a global outlook is good at the end of your problem, but when you're solving the problem, you're looking at one thing at a time. So in this experiment, OH minus concentration is constant, therefore it has no effect on the rate. But the ClO2 concentration is 3 times higher in experiment number 1. So if we look at the rates, we get 0.0248 divided 0.00276. If you kindly stop talking, the microphone will pick it up. And that equals about a 9. Therefore, the reaction is second order with respect to the chlorine dioxide concentration. That's the first part of the answer. So that was worth 1, 2, 3, 4, 5, 6, 7 marks. And where did I attribute it? I wanted 1 mark for this, for you to recognize that you had to look at OH, that it had no effect. I gave you 1 mark for recognizing that the next thing to look at was chlorine dioxide, that its concentration was 3 times higher, and that the difference in rates was 8.98, which is really equivalent to a 9. And lastly, to recognize that it was second order. So that part alone was worth 7 marks. The second part was to analyze experiments 2 and 3. Of the same question. And in this one, it's chlorine dioxide which is being kept constant. Therefore, it also has no effect on rate as far as chlorine dioxide is concerned. So that means we can turn our attention to the other thing in there, which is the hydroxide. And the hydroxide concentration triples. The effect on the rate is 0.00828 over 0.00276, which is 3 times faster for the higher concentration. Therefore, the reaction is first order with respect to hydroxide ion concentration. Where did I attribute marks into that explanation? I wanted you to recognize that you had to look at chlorine dioxide, that it had no effect on the reaction, that you had tripled the hydroxide within those same experiments, and that you were comparing the initial rates of the reaction, and that it gave you a 3 times difference, which means that the reaction is first order with respect to that reactant. And from there, you were to construct the rate law. And the rate law in this case is rate equals the rate constant K times the hydroxide concentration times the chlorine dioxide concentration to the power of 2. And each one of those parameters was worth a mark. So you got a mark for putting rate, vertical rate constant for the hydroxide, for the chlorine dioxide, and for the correct power. Total on this number, which is number, it's 1428, number 2. Is there a part C? Yeah, there is a part C. So let's do the part C as well. In part C of 1428, it asks the question, calculate the rate when chlorine dioxide concentration equals 0.01 molar and hydroxide concentration equals 0.025. So you simply have to plug it into the rate law. So this is B, this is A, and again, this is 1428 we're looking at in the book, which is Brown and others. Cover so equations times the chlorine dioxide concentration. Why am I writing this the second time right below? Because that alone was worth 1 mark. If you just got that far, I gave you a mark. Then, the value of I skipped over something. Let me backtrack. It asks in part B to find out what the value of K is. So if you even just took one of the parameters and plugged in the numbers, you would have gotten 230. All of them give you 230. But I did all 3 of them, and well, one of them gives a slightly different number. One of them gives 229.6. The other ones give you 230. So I'll show you what I did for each calculation. You can rearrange this to solve for K because that's what it's asking you for. So K is equal to the rate divided the OH minus concentration times the chlorine dioxide concentration squared. And you get 3 calculations. So in number 1, K equals 0.0248. Now you didn't have to do all 3. I was content with 1, but I did all 3 because I wanted to cover all the possibilities that any student could possibly entertain. So in the first case, you would get 229.629 recurring meters to the molarity to the -2, seconds to the -1. If you took the second set of data from the second experiment, you got K is equal to 0.00276 over 0.30 times 0.20 squared. That would have given you 230. It's a nice feeling to do the calculation 3 different ways and get the same answer 3 times. It tends to confirm you that you're on the right track. And the third one yields the following result. Still get 230. So you were expected to report that to 3 significant figures, and that's what you get. So the way I attributed the marks on that one, it was this part A was worth 18 marks. Doing it in red. Part A was 18 marks. Part B was 9 marks. So the 9 marks would have been to, but don't let it mislead you. If you got this, I counted it as if you had done all that. Just to get 230, that's the answer I wanted. So, you know, there were people who got various levels of success, so they would get part marks. That's why it's always a good idea to write anything that you think you know, because it gives me something to work with so you can get part marks. Part C now, it asks what the result would be under a given set of conditions. So under those conditions, number 2C, rate is equal to the K times OH minus, same rate law, times the chlorine dioxide concentration squared. And you know the rate constant because you just finished calculating it in the last exercise. And you're told the hydroxide concentration is 0.025. And that the chlorine dioxide concentration is 0.01 molar in each case. So your answer will come out to be 5.75 times 10 to the -4 molarities per second. The way I marked this one was 1 mark for the rate law, which you already knew from the last equation, and then 1 mark for each one of these parameters, and 1 mark for the final answer for a total of 6. So the total for number 2 was 33. I'll uncover that on the board later. Now we're going to the next question. which is 1439. I'm only going to show you one way to do it. There's a graphical way of doing it, but it just takes too much time, and you end up getting exactly the same answer. When would you prefer to use a graphic way of solving 1439? When your data is a bit scattered. So with most real life experiments, your data doesn't always follow a perfect set of parameters. You always have some interference. You know, maybe when you prepared your solutions, you weren't as accurate, or you had an extra drop clinging into the pipette when you were pipetting. All things like that can affect the accuracy of your results. But by and large, you can still determine what the value of K is, especially if you do enough data points. They tend to average out what the true value is. And that's why in science you always repeat experiments. That way the noise tends to cancel out, and the real results tend to become more prominent. Because as you know, or maybe you don't know, noise is random, and random things tend to cancel, whereas real data tends to add on top of itself, and you see it more and more clearly. They exploit that idea in something called the Fourier transform application. It's a mathematical application to enhance data. So if you have a very weak signal, you can overlay 1,000 copies of the same weak signal, and because noise is random, it tends to cancel out, whereas a real signal will tend to add up. So you'll start seeing the signal growing, and you can use this electronic technique, this mathematical electronic technique, to enhance very weak signals. And they do that for detecting very weak things, both in chemistry and probably other areas. All right, so question 1439. It talks about the reaction of thionyl chloride, a gas, turning into sulfur dioxide and chlorine gas. It's first order in thionyl chloride concentration. Using the following kinetic data, determine the magnitude of the first order rate constant. So when you have a first order reaction, you can use A is equal to A naught e to the KT, where A is the concentration at some time t. A naught is the concentration at time equals 0, the beginning of the reaction. K equals the rate constant for the reaction. And T is obviously the time with the correct units used. So we rearrange this equation by transposing the A naught to give you e to the KT. Plug in the values. 0.803 is one of them, and it starts off at 1, and then e to the k, and the time interval is 10,000. So I took the biggest time interval, or is it 29? I took the biggest time interval that caused the biggest change, so from 0 to 10,000 seconds. So basically, I let the reaction run as far as I could to use the biggest span of data, but probably it would have worked with any one of the spans in between. You don't have to use the biggest one, but I just thought that's playing it safe to use the biggest span of data. And the time interval was 10,000 seconds. Take the ln of both sides. So you get ln of 0.803 equals ln of e to the k 10,000. But when you take something, the natural log of something that's already raised to the power of e, it basically gets rid of e. So you get 10,000 k. And when you transpose that, well, first let's put down the value of ln 0.803. It's negative 2.194,00565 times 10 to the minus 1, and that equals 10,000 K. So K ends up being negative 2.19 times 10 to the minus 5 seconds to the minus 1 after sig phase. How did I attribute marks to this one? You got 1 mark simply for writing the equation correctly, 1 for transposing it, 1 for plugging in the values, and 1 on both sides, obviously, and then doing the arithmetic. I skipped 1 step in there that you still would have got marks for, and then the final answer. So the total up to 10. You could have also done it graphically, but I don't think anybody undertook doing it graphically. And I'll show you the example. Comes up with a straight line. You take the slope of the line, and the graph is ln of A versus T. Take the slope of the line, you get this number. And when I did it, I got negative 2 I got exactly the same number, because as it turns out, when you take the slope of the line at the very ends, it ends up being the two endpoints anyway. So it's like doing this calculation over, but just with a different approach. If the data points were a little bit scattered on either sides of the line, you would get different values of k if you did it this way. But with using a graphical interpretation, it tends to average out the error. You tend to get a better result, in my opinion. Going back to this board now. '53 in the book is our number 4 in the test. So it asks, a certain first order reaction has a rate constant of 2.75 times 10 to the minus 2 seconds to the minus 1 at 20 degrees Celsius. What is the value of K at 60 degrees Celsius if the energy of activation is 75.5 kilojoules per mole? So this is a situation where you have two sets of data, and they tell you what the conditions are at one set of data and what rate constant it gives you, and then they want you to find out what the rate constant is at a different temperature. So when you have two sets of data, the best equation to use, although you didn't have to do it that way, is this one. Ln of K1 over K2 is equal to the activation energy divided by the constant, gas constant, times the reciprocal of the second temperature minus the reciprocal at which the K values are obtained. Now, you could have used this one. K is equal to A E times the e to the power of the activation energy over RT, and then you can calculate what the steric factor is. The steric factor you assume is the same at the different temperatures. Some of you did that, you got it right, and I marked it 100% on. But you see, if you use this one, because the steric factor is the same in both cases, you can just cancel it. It doesn't even come up in the calculation. And that's what I did, because I thought it was faster. So ln of 2.75 times 10 to the minus 2 is the value of K1. K2 you're trying to find. EA has to be converted to joules. If you put it in as kilojoules, you'll create an error of 1,000-fold. You got to put it in joules. So it's going to be 75,500 joules per mole. And the value of R is 8.314 joules per Kelvin mole. Temperatures are in kelvins, so I converted those to Kelvin. You got to use the absolute temperature scale to get the right answers on this. If you enter the Celsius temperatures, you're going to automatically get a wrong answer. So that comes out to ln of 2.75 times 10 to the minus 2 over K2 is equal to 9.081. I'm just going to write you all the numbers that came out in the calculator without any truncation error, no rounding error during the calculation. You never round during the calculation, you only round at the very end. I know it's tedious, but if I didn't show you how to do it, somebody would imitate me and then you'd get rounding errors. So ln of 2.75 times 10 to the minus 2 over K2 equals, something in there was a negative, and I put it, yeah, I think this number comes out negative. that number is bigger than this number. And then what you get is negative 3.719, 351, 355. And I take the ln of both sides, or the inverse ln of both sides. And what you get is 2.75 times 10 to the minus 2 over K2 equals 2.42496, 9219 times 10 to the minus 2. When you transpose the value, so you bring K to this side, you bring 2.42 to the outside, you get K2 equals 1.134035. 0.13, you're only allowed 3 sig figs, so you report it as 1.13 seconds to the minus 1, and that's what I was looking for as the final answer, which was at the back of the book. So if you got that, you got 1 mark, because you have to show all the other stuff. That's why, you know, you guys think you have a break when I give you an open book test, because you have this book and you're holding onto it like a security blanket, but it's not really helping you if you haven't done the practice at home. It creates a false sense of security, and you realize it as your panic mounts, as you leap through the pages realizing you're not prepared. It's not a nice feeling, and I don't wish it on you. So that was worth 12 marks. All right, so if you put all of that together, let's rewrite it over here. No, actually, I have it in blue. So this one was worth 33, this one was worth a total of 10, this one was 12, so the total of all that is out of 77. Okay? So I think maybe next Monday we should redo it. Give you some time to read through the chapter again, try a few sample problems from the ones I gave you. I won't give you the exact same questions because that's not going to be fair, but I'll give you something similar to this. Okay, 4 questions, you get a chance to get 100% again, great. If you don't want to write it, you don't have to, but I recommend you do it anyway, because when you repeat stuff, you remember it better.